Hey, welcome. Again, I'm Kurt Killian from Missouri State University. This video is on the subtraction of fractions. I'll just give you the standard kind of thing again, is that you can pause whenever you need to because this video can get a little bit long. Get some materials out, try it as we're going through, review the video, just pull up the PowerPoint if that helps, because the PowerPoint has an awful lot of information in it if you don't want to watch the video again. So we'll start just like we did with the addition. This is going to be standard kind of organization. We're going to do a word problem, we're going to do Cuisenaire rods and the area models, and then we're going to look at a matching paper and pencil algorithm. Again, when you're making the word problem, we're going to focus on only one operation at a time so we can really look at the structure of that word problem, what makes it subtraction. You're going to look for a removing or a takeaway kind of thing, even though there are other kinds of subtraction situations. There's missing add-end and comparison kinds of things that you can do. And in fact, some of the Cuisenaire rod models look more like comparison than they do takeaway. But we're just going to focus on takeaway kind of situations just to get us started. The most important thing about subtraction in the structure of the word problem, and you'll see as we get there, is that it must involve a removing of a portion of a whole. And you can't do a portion of a portion that ends up being multiplication. We'll compare that when we get to the multiplication video. But we must have a context that uses a half of a whole cup of milk, or a half of a whole pound, or 2/3 of a whole cup of sugar or something. It's always of the whole that we're operating with. So here's the first example of a word problem. Joe has 2/3 of a whole cup of milk. The recipe calls for half of a whole cup of milk. That one's in the red there, that's the one that's essential, that it must be the whole. And then you ask at the end, how much of a whole cup of milk will Joe have left? Again, the key attributes are you're always, in this case, it's a takeaway kind of situation. You're always removing something. You always want to know how much is left. It's always how much of a whole is left, because that turns out to be the only appropriate question, because you want to know how much milk the person has at the end, and that's legitimately measured in whole cups. For takeaway, you must remove, again, some portion of the whole unit. This is especially clear in the context of cooking, and so if you want to start with a context that makes that very obvious, cooking is a good example, and you'll see in this context here, the recipe calls for half of a whole cup of milk. It would not be normal or subtraction or legitimate if you said that the recipe says to go to the refrigerator and use half of all of the milk that you find in there. It's never half of what you have. It's half of a whole cup of milk. That's the context. It only makes sense to ask that, and so since that's an important part of subtraction, it might help to start with a cooking context, because that's really the only appropriate thing to say. So again, here's the word problem. Again, we're starting with 2/3 of a whole cup. We're going to use half of a whole cup, and we don't know how much of a whole cup is left. We're going to, for the Cuisenaire rod model, make the wall again. And of course, that wall will need to have thirds and halves in it, since that's what's involved in the problem. And then we'll act out the situation using a linear approach, because Cuisenaire rods are like a linear model, where we'll start with 2/3 of a cup and remove a half of a whole cup, and then we'll measure that. So making the wall, there's an example on the PowerPoint also, that the wall that we have here on the document camera is pretty much the same, although again, it doesn't really matter where you put these. Some people put the single blocks at the bottom. I usually put them at the top, but it doesn't really matter. As long as you can see what the whole is, and you can see what the halves are and what the thirds are. And again, this is a third because it takes 3 of them to make the whole. So we've got a wall, so we know what the fractions look like. And then we just do what the situation says. Joe has 2/3 of a cup, so we just pull out here what Joe has. Joe has 2/3 of a cup. Move this over a little bit. And the recipe calls for half of a whole cup. Well, we know what a half of a whole cup looks like, so it uses this much. And we're doing this as a linear kind of model again, so that we're thinking about from here to here, is the whole 2/3 cup that we started with. From there to there is the half a cup that's being used. And we want to measure to see how much is left over, and we just typically measure with single blocks. And so we can see that there's one block left over. But how big is that block? That's why you want to refer back to the wall, keep the wall intact, and notice that's 1/6 of the whole. So it looks pretty clear that there's 1/6 of a whole cup left over. One of the things you might notice is that there are alternative modelings, and it's especially important if you ever wanted to draw this for some reason, like for assessment or something. But some people will model on top to show like it's covering up. Can you see that in the document camera? We're just covering up with a half a cup to show that a half a cup has been used, and then we measure to see how much is left over. But you see, if you model like that and you try to draw that, that's not drawn very well. So I typically model it down on the flat rather than covering on the top, just because it would fit the way you'd want to model it. And again, it looks a little bit like a comparison, that we're comparing 2/3 and 1/2 and seeing what's the difference between them. But you can treat it as subtraction, like here's what you start with. I use from here to here. I've used all of that. This is how much is left over. So for the area model, let's leave it on the document camera. We again do the same three things as we did with addition. We're going to draw the unit, then we're going to subdivide appropriately to see what is involved in the word problem. In this case, we're going to show 2/3, and then we're going to have to find out what a half of a whole looks like and remove it, and then count to see how much is left. So we'll start by drawing the unit. That's pretty easy. You just make a rectangle. I know this doesn't look like a cup of milk. It's a semi-abstract kind of model, but we're using a rectangle because it's really easy to see two different dimensions in it. So Joe has 2/3 of a cup. So you do a subdivision as close as you can to getting 2/3. And I always do this part out here to show I do not have any milk out here in this part of the cup. So there's no milk there I can use from. All I have is 2/3. I don't have anything out here. So I'm showing that as kind of like it's invisible or not quite there. The recipe calls for half of a whole cup, so we do a subdivision in the other direction so I can see what half of a cup looks like. And you can, again, if you want, make that look like I don't have any milk out there. And notice that a half of a cup is, because it takes 2 of those to make the whole, a half a cup is all of this. That's 3 whole pieces. So half of a whole cup is 3 pieces. So when I remove or use the half a cup in the recipe, I'm going to use 1, 2, 3 pieces. I'm actually going to show it like it's a takeaway with an arrow to show that part is being removed, because that's a half of a whole cup being removed, not half of what I had, because recipes wouldn't say to use half all the milk you find. It says use half of a cup. So that's gone. There's 1 piece left over, and so obviously 1 piece, but how big are those pieces? Well, there's 6 to make the whole, and so that's 1/6 of a whole cup that's left over. See, I have to zoom through the rest of this. So we did the subdividing to see the thirds, and we shaded 2 of those, or paid attention to 2, or got rid of the other part that is not involved, and then shaded to show what was being removed, and just count to see that there's 1 left over. Okay, let's look at the paper and pencil algorithm that would fit that. Try this one. So I'll do that since this model is already up here. Notice that this problem was starting with 2/3 of a cup, and we're removing a half of a whole cup. So what really happened? Well, we can see in the Cuisenaire rod model, what we're going to write down as a record of what we did should grow out of what happened up here. So, sorry, in the area model here, what happened? Well, 2/3, we renamed it, just like we did in addition with an equivalent fraction. That 2/3 became 4/6. And the half, when we redrew it here, the half was 3/6. Of course, I had to take the 3/6 from the milk that I had. Can't take it from out here because there was no milk out here. And ran out of space here. Again, just like with addition, when we get common denominators here, this is like asking what's 4 apples, take away 3 apples, it's 1 apple. So what's 4 sixths? Those objects called 6, take away 3 of those same objects, we're down to 1 of those objects, which is 1/6. So again, notice it is a Cuisenaire, it is a common denominator kind of algorithm. It fits the way we did it, and I'll just show you that back here to show that it does work on the Cuisenaire rods also. You can see that 2/3 here actually was 2/6 in the wall, or 4/6. 2/3 is 4/6. 2/3 here, if you'd measure it back in the wall, is 4/6. The half is 3/6, and so what's left over is 1/6. So you can see that same algorithm showing up inside the Cuisenaire rod model too. Just point out one more time that the way of looking at this paper and pencil algorithm is this is not the real math. Oh, look at this. So this paper and pencil algorithm here is not the real math. It's just a record of what you already knew how to do at a concrete level. And so you need to make sure that what you do as an algorithm really does fit what you did at the concrete level. Again, you can see the Cuisenaire rod stuff there. So we already made sense of it at a concrete level. This is just a record of what we already know how to do. Okay, let's try a, well, this is just some more comments about the Cuisenaire rod model. We've already really talked about that. They're both common denominators. It's like turning it into whole number problems, so we've already discussed that. So here's a new word problem. My mother has 3/4 of a whole pound of platinum. She has to sell 2/3 of a whole pound of platinum to send my brother to college. Notice again the red marking there to show that it has to be 2/3 of a whole. It's not that she's selling 2/3 of what she had, because we'll see later that makes it multiplication. And the standard question is, how much of a whole pound of platinum will she have left? Because platinum is expensive. We want to know how much she's worth in terms of platinum once she's sold 2/3 of a whole pound. So again, the key attributes, this is a takeaway. We could do comparison. It's always asking how much is left compared to the whole, and we're clearly removing a portion of the whole. We're removing 2/3 of a whole pound of platinum. So again, when we model this with Cuisenaire rods, we're going to make the wall, we're going to act out the situation. We'll start with the 3/4 of a pound, and then we'll see what 2/3 of a pound looks like, whole pound looks like. We'll remove that and then measure and count to see what's left. So let's model that. So we need a wall again that has a hole in it that has both thirds and fourths, since thirds and fourths were involved in the problem. And you'll notice the wall on the PowerPoint is slightly different. It just has the single blocks on the bottom. That doesn't matter too much. And notice that we did have to, just like we did on the second edition one, had to make a unit out of 2 different blocks because it requires a 12 rod in order to get both thirds and fourths. We made it with a 10 and a 2. You could use anything that adds up to the same length of unit. So then we just act out the situation. See, my mother has 3/4 of a whole pound, so 3/4 of a whole pound looks like this. And she's going to sell 2/3 of a whole pound. Well, we can tell from the wall exactly what 2/3 of a whole pound looks like. So she's selling this much. And we just want to measure to see how much of a whole pound of platinum is left over. In this case, we measure, we'd probably do lots of other examples, and you're going to do examples probably too, and you'll get some where you don't have just one block left over. It was by luck we got the same block left over every time, with just one block. But notice this block is one piece, but how big a piece is that? That's when you have to go back to the wall and notice that is 1/12 of the whole pound of platinum. So there is 1/12 left over. All right, we'll go ahead and do the area model. So do it the same way as before. We're going to draw the unit. We're going to subdivide it to see what 3/4 looks like. We're going to subdivide it so we can see thirds, so we can remove 2 of those. Excuse me, and then we're going to count. So we draw the hole again. I don't know what a pound of platinum looks like, but we're going to make it look like a rectangle. And my mother has 3/4 of a pound, so we need to see what fourths look like. And she has 3/4, so she does not have any platinum out here. Just to do that to keep me from taking any platinum from out here when I have to sell the 2/3 of a pound. So I could shade this if I want, but I don't need to because I can see that I've got everything but that. And then she is, let's see, the next thing we're going to do is find out what thirds look like, so I can remove 2 of them. It does say to shade 3 there, but you don't have to if you don't want to. Sell 2/3 of a whole pound, so I need to do subdivisions this way so I can tell what thirds look like. Again, you can show that as invisible, so we don't have any, no, we don't have any platinum there. And we're selling 2/3 of a whole pound. Well, notice 1/3 of a whole pound was this because it takes 3 of those to make up the whole. 1/3 of a whole pound is 4 pieces. So when I give away to sell the first 1/3 pound, I have to get rid of 4 pieces. So I shade 4 of those. I like to do this just like we did on one of the addition ones, is show that's the first. You can put ones all the way through there if you want. That's the first 1/3 pound. But we have to get rid of 2/3. So we have to do a second 1/3, so you can shade however you want with that second one, but notice it takes 4 of them to actually get a whole 1/3. And if you want, you can label those as 2, 2, 2, 2 to show that's the second 1/3. And then notice that that is being removed, so I need to show this like a takeaway. Makes it very clear conceptually, concretely, that we've removed that. And it is clear that there is 1 piece left. But how big is that piece? Well, if you look at the whole pound of platinum, it takes 12 to make up a whole pound, so that's 1/12 left. That looks pretty similar to what's on the PowerPoint. Okay, what about a paper and pencil algorithm for this? Move it up just a little bit. Notice that the original problem was we're starting with 3/4 of a whole pound. We're removing 2/3. And what did it really happen? Well, it's especially clear in the area model that this 3/4 here was this piece. I don't have this out here. That's 3, 6, 9 pieces. So 3/4 actually becomes 9/12. And again, kids, if you've done the right amount of work ahead of time, they would be comfortable with that equivalent fraction work, and it won't be any problem at all for them to say, oh, I know 3/4 is equivalent to 9/12. And then we subtracted 2/3, but what did 2/3 become? Well, notice 2/3 were these pieces here. That's 4 8 pieces. So when we take away 2/3, we're taking away 8/12. A little hard to see that. So we really have 9/12, and we're removing 8/12, and clearly that's just like taking away 8 apples from 9 apples. We have 1 apple left, but they happen to be 12ths because it's a 1/12 of the whole. So that 1/12 gets pretty clear. And again, that's a common denominator kind of algorithm. It grows out of material level. We'll show you what it looks like on the Cuisenaire rods. It's going to be a little hard to see the whole thing here. It's a lot clearer in the area model, but you can see it in the Cuisenaire rod model too. Notice that 3/4 here, if you count, really becomes 9/12, and 2/3, if you count, see where that comes out up here, really becomes 8/12. So when you do the comparison here, or the subtraction, removing here, you're really comparing 9/12 and 8/12, and there's 1/12 that's left over. So the paper and pencil algorithm is consistent with common denominators that you're used to doing. But in this case, it makes sense. We didn't teach it first. We're developing this late. By the way, we talked about it in the addition algorithm. When we teach the paper and pencil, that should come late. It should all grow out of what you do at a concrete level so that the kids have internalized, what those operations really mean with these kinds of models. And then the algorithm is just a way of recording what you've already made sense of. So here's a few notes, things related to subtraction that you might want to pay attention to. Again, just like in addition we talked about, it's really nice to encourage estimation and then compare to the exact result when you actually model it. In this case, it's reasonable to expect an answer pretty close to 0. The one we just did, the 3/4 take away 2/3. 2/3 is pretty close to 3/4. It's smaller, and so you take it away. There's just a little bit left over, and so getting an answer of 1/12 is not really out of reason. You ought to encourage kids to be doing estimation on this all the way through. For the area model, it needs to be absolutely visually clear that 2 different thirds have been removed. So if we go back and look at this area model, see how we shaded each of the thirds separately? If you just shaded all those in with the same kind of shading and you had 8 blocks there, it's not so clear that we've removed 2 objects of a certain kind, that we've removed 2 of those thirds. So shade each third separately. Also, if the subtraction starts with more than 1 unit, suppose it was 1 and, I'll just do the whole thing over again. Suppose it was 1 and 3/4 take away 2/3. Well, you just start with 1, and we had 4ths and thirds, so we're going to do the 4ths this way. And so we had 1 and 3/4, so we have the whole plus another whole here that has 3/4, but nothing out here. What I'm trying to point out is that the modeling is not really going to be too much different. You just have to have a unit stuck out at the beginning. She's selling 2/3 of a whole pound, so we need to know what 2/3 of a pound looks like, so you do the subdivisions in both of them. Noticing you don't have anything out here. And in this case, you just have to remove 2/3. Well, you have a couple of options. Typically, we remove the 2/3 from over here just like we did on the previous one. And so since a third is 4 pieces, I'm going to remove 1, 1, 1, 1, and 2, 2, 2, 2, and show that being removed. And then you can count and see, there's a whole left, but still 1/12 left over here. Now, when you have a unit, though, some people may instead say, well, I could have instead, since it's so conceptually clear that this is 2/3, I can just remove it from there. And then count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 pieces left. But those pieces are 12ths because it's a 12th of a whole. Still, this is the whole. This is not the whole. That's the whole. That's the whole pound of platinum, and we have 13 pieces where it only takes 12 to make it, so you can see from there still that you get either 13/12 or 1 and 1/12 left over. So either of those will work when you have mixed numbers. Mixed numbers are a little bit easier to take the subtraction away because you can see the thirds clearly. Now this one, since the thirds are clear, you don't need to shade each of those separately because it's clear the thirds were there because of that red subdivision. But for the one that we did here, each of those thirds has to be shown separately to make it clear that you've removed 2/3. So you can adjust fairly easily if the problem happened to involve mixed numbers. I mentioned this before, but it's best not to destroy parts of the wall so you can still have a reference back to know what the whole and what the thirds and what the fourths were. And if you're going to draw the rods, you may not need to, but if you need to for assessment purposes or something else, or people are working on it, virtual rods, and they need to have a record of what they did if they can't print it out, just make sure that you don't have kids trying to draw the rods without having made it with the rods first. It's really important. They must do it at the concrete level so they can see how those rods fit together based on their relationship. If they try to do it without making the model with the rods first, they'll end up having to work at a very abstract level and do it very numerically, and they'll miss the point. They'll miss relationships. So strongly discourage trying to draw pictures of walls before they've actually, or pictures of the Cuisenaire rods before they've actually modeled it and seen what it looks like at a very concrete level. Okay, that's all we have about subtraction. Again, I would recommend that you practice some on your own. Review the video if you need to. Come to class prepared with questions. Thank you.